Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to talk on module Fourier Transform Infrared Spectroscopy, which is FTIR Principles and Instrumentation under the paper Characterization of Materials Part 1. So students, let us see what we are going to learn in this module. We are going to learn first of all about the principle of the FTIR, the principle on which the instrument taking the Fourier transform under the infrared radiations is based on. Secondly, we'll study about the instrumentation of the FTIR system, that is what are the various components of the FTIR system. Then thirdly, we'll study the fundamental components of an FTIR system, and in the end, we'll take the various examples of the various molecules, that is which are polyatomic, for example CO2 and water, and see how the FTIR of these molecules appear on a graph. So before getting into the details, let's have a brief introduction about the principle of the FTIR. Infrared or IR spectroscopy is an important system in organic chemistry which can identify particular functional groups present in the molecule. Additionally, the unique group of absorption bands can readily ascertain the characteristics of pure compounds and also locate specific impurities. Infrared spectroscopy works on the principle that the molecules vibrate at a specific frequencies. These frequencies, approximately 4000 to 200 centimeter inverse, fall in IR portion of electromagnetic spectrum. When infrared radiation or the IR radiation is incident on the sample, it absorbs radiation at frequencies similar to its molecule vibrational frequencies and transmits other frequencies. Frequencies of absorbed radiation are detected by infrared spectrometer, and a plot of absorbed energy against the frequency is called infrared spectrum, which can be obtained. Since dissimilar materials possess dissimilar vibrations and give distinct infrared spectra, so a particular molecule can be identified. For example, a nonlinear molecule which has n atoms exhibits 3n-6 vibrational motions for its atoms, also called fundamental vibrations or normal modes. Only those vibrations appear in the IR spectra which are IR active. IR active means which absorb IR light. For a mode to be IR active, the vibration must induce a change in its dipole moment of the vibrating molecule. Therefore, symmetric vibrations do not appear in IR spectrum. In a molecule with center of symmetry, vibrations symmetric with respect to the center are IR inactive.
Harmonic oscillator is usually employed to model these vibrations, as is shown in figure 1, wherein a chemical bond is depicted as the spring linking between two point masses. Spring tension K denotes the bond strength or molecular force field, and the mass of the atoms or chemical groups is represented by the point masses M1 and M2. The frequency of oscillations Nu is expressed as nu is equal to 1 by 2 pi c multiplied by square root of k into m1 plus m2 by m1 m2. Thus, the bond strength decides the vibration frequencies such as triple or double bonds cause higher frequency than the single bonds. Consequently, frequencies are highly sensitive to the type of chemical group, electronegativity of the adjacent atoms or molecules, and the interactions involving hydrogen bonds. If one atom is involved in hydrogen bonding, the bond will be weakened, causing a downshift in the stretching mode frequency. Therefore, the stretching mode frequencies can provide structural details of certain chemical groups such as carbonyl or carboxylic in proteins. This can be achieved by monitoring the formation or disruption in hydrogen bonds. Another factor affecting the vibration frequency is mass of the atoms involved in vibrations. Consequently, the vibration frequency can also be altered by isotope labeling of the atoms involved. Thus, depending upon the type of atoms present, a specific chemical or functional group exhibits vibrational frequencies in particular region. Again, the frequencies in these regions are affected by the environment or the solvents of the chemical group. Thus, a detailed analysis of simplified model compounds in varying environments is required for establishing a clear relationship between the IR mode frequency and structure of the compound. Moreover, from absorption frequencies, the presence or absence of various chemical groups in a chemical structure can be ascertained. Other than the characteristic position of the absorption peaks, their magnitude is concentration dependent. Therefore, both quantitative and qualitative information can be obtained.
Fourier transform infrared spectroscopy or FTIR spectroscopy is meant to overcome the difficulties experienced in dispersive instruments. An important limitation was the long time required for the scanning process. It is desirable to simultaneously measure all IR frequencies. So the solution used is a simple optical device called interferometer to produce a signal composed of all infrared frequencies embedded within it. The signal is recorded very rapidly, typically within a few seconds. Therefore, measurement time per sample was abridged to a few seconds. Interferometers generally use a beam splitter to split the incoming IR beam into two optical beams. One beam is reflected off a flat mirror that is fixed, while the second beam is reflected off of another flat mirror which is on a system, allowing this mirror to shift some distance away from the beam splitter. Both the beams reflect off of their respective mirrors and then reunited when they assemble again at beam splitter. Since path of one beam is fixed and for another is continuously varying, when its mirror shifts, the signal existing or exiting the interferometer is result of these two interfering beams. The resultant signal is described as interferogram and exhibit such property that each data point on the signal contains information of all IR frequencies coming from the source. Consequently, all frequencies are simultaneously measured when the interferogram is recorded. In this way, the interferometer leads to extremely quick measurements. Since a frequency spectrum, that is, frequency spectrum is the curve between the intensity and the frequency, or the intensity versus frequency plot, is required for analyzing the compound. The recorded interferogram cannot be directly interpreted, and some methods to decode individual frequencies are necessary. This decoding is achieved by using the well-known mathematical technique which is called as Fourier transformation, and the result of the transformation provides the required spectral information for further analysis.
The resultant signal is described as interferogram and exhibits such property that each data point in the signal contains information of all IR frequencies coming from source. Consequently, all frequencies are simultaneously measured when the interferogram is recorded. In this way, the interferometer leads to extremely quick measurements. Since a frequency spectrum, that is, intensity versus frequency plot, is required for analyzing the compound, the recorded interferogram cannot be directly interpreted, and some methods to decode individual frequencies are necessary. This is achieved by using the well-known mathematical technique called Fourier transformation, and the result of the transformation provides the required spectral information for analysis. Students, now let us see the instrumentation of the FTIR spectrometer. The essential components of an FTIR system are included in Figure 2.2. IR source emits a broadband radiation having various IR wavelengths. Usually, a silicon carbide ceramic is heated around 1550 Kelvin is used as IR source. Rather than a monochromator, a Michelson interferometer is often employed to analyze the infrared beam after passing through sample. The IR radiation passes from the interferometer, which modulates it by performing optical inverse Fourier transform on this radiation. Modulated IR beam is then passed from a gas specimen which absorbs it at different wavelengths due to different molecules present in it. Finally, a detector detects the intensity of IR radiation. A computer digitizes and performs Fourier transform on detected signal to produce IR spectrum of gas sample. Students, now let us see the fundamental components of an FTIR system. First, the source. A glowing black body emits the IR radiation. This beam is passed to an aperture that limits amount of energy incident on sample. Second is the interferometer. Interferometer performs spectral encoding on incoming radiation, and exiting signal contains all the IR frequency components. Third is the sample. Beam is either transmitted through or reflected off the sample surface, depending on type of investigations being performed. Sample absorbs energies at frequencies characteristic to it. Fourth component is the detector. The detector measures the interferogram signal. And fifth component is the computer. It performs Fourier transformation to obtain final IR spectrum for examination. The components of optical system in FTIR spectrometer include an interferometer which has two mirrors, IR source and IR detector, and finally a beam splitter. Beam splitter, a half-silvered mirror, is central to the functioning of the interferometer. When light is incident on it, half of the light is reflected while the remaining half is transmitted. The rotating mirror and stationary mirror of the interferometer both receive each half of these beams. These beams again reach the beam splitter after being reflected from the two mirrors. The beam splitter again splits each half beam into reflected and transmitted half beams. Two output beams result. One travels to the source and the other to the detector. When these two beams come back to the beam splitter, an interference pattern is generated, which is called as interferogram. The displacement of the moving mirror causes difference in path length in the two arms of the interferometer, which in turn varies the interference pattern. The interference pattern is detected by the IR detector as variations in IR energy level and ultimately yields spectral information.
Thus, the light entering the interferometer from the source is either sent back to the source or directed towards IR detector. The moving mirror, while scanning back and forth, causes greater or less than half of total light entering the interferometer to reach the detector. The light which does not go to the detector is sent to the source. There is no other sink of the light. If the mirror in interferometer are equidistant from beam splitter, then both light beams travel the same distance. When these beams return to the beam splitter, each of them is again split and recombined with half of the light from the other arm of the interferometer. The two components beam which are sent to the detector as output are entirely in phase with each other, leading to constructive interference. Whereas the two component beams sent to the source are completely out of the phase to each other, which results in destructive interference. Thus, the entire incident light reaches the detector and none reaches the source. On the contrary, if moving mirror is displaced by lambda by 4, where lambda is the wavelength of the incident light, the light moving from moving mirror coming to the beam splitter lambda by 2 out of the phase with the light from the fixed mirror, which causes the destructive interference in the component lights reaching the detector and constructive interference in the components reaching the source. Thus, no light reaches the detector and entire light is sent back to the source. Thus, with the back and forth movement of the moving mirror, the detector perceives light and dark bands, resulting in total or partial constructive destructive interference. In this case, interferogram is a cosine function having full intensity when both mirrors are equidistant from the beam splitter, to zero intensity when there is lambda by 4 part difference between them. If the moving mirror is displaced by lambda by 2 or multiples of lambda by 2, then also full intensity in output is obtained. Likewise, a displacement of lambda by 4 or multiples of lambda by 4 result in zero intensity. We can see these constructive and destructive images and the interference in the figure given below. Since the IR source is polychromatic, it emits light with a wide frequency range. Each emitted frequency produces a separate cosine signal, and the resulting interferogram is sum of all cosine waves produced by each individual IR frequency. In this case, complete constructive interference occurs only when both mirrors are equidistant from the beam splitter, as at this point all waves simultaneously interfere in constructive manner. At all other points, there is only a partial constructive interference. The frequency as well as the intensity of each cosine wave present in the interferogram is resolved by Fourier transform. Thus, a plot of intensity as a function of frequency is obtained in the form of a spectrum.
If the mirror in interferometer are equidistant from beam splitter, both light beams travel the same distance. When these beams return to beam splitter, each of them is again split and recombined with half of the light from the other arm of the interferometer. The two component beams which are sent to the detector as output are entirely in phase with each other, leading to constructive interference, whereas the two component beams sent to the source are completely out of phase to each other, resulting in destructive interference. Thus, the entire incident light reaches the detector and none reaches the source. On the contrary, if moving mirror is displaced by lambda by 4, where lambda is the wavelength of the incident light, the light from the moving mirror coming to beam splitter is lambda by 2 out of phase with the light from the fixed mirror. This causes destructive interference in the component lights reaching the detector and constructive interference in the components reaching the source. Thus, no light reaches the detector and entire light is sent back to the source. Since the IR source is polychromatic, it emits light with a wide frequency range. Each emitted frequency produces a separate cosine signal, and the resulting interferogram is the sum of all cosine waves produced by each individual IR frequency. In this case, complete constructive interference occurs only when both mirrors are equidistant from the beam splitter, as at this point all waves simultaneously interfere in constructive manner. At all other points, there is only a partial constructive interference. The frequency as well as intensity of each cosine wave present in the interferogram is resolved by Fourier transform. Thus, a plot of intensity as a function of frequency is obtained in the form of a spectrum. Figure 5 shows a hypothetical spectrum having three frequencies with different amplitudes. The middle figure shows the interferograms for these frequencies, and the bottom portion shows the interferogram for the three mixed frequencies.
So students, let us now summarize what we have learned in this module. First of all, we learned about the principle on which the FTIR works. Secondly, we studied in detail about the instrumentation. We studied in detail about the fundamental components of an FTIR system, and then we took few examples of the polyatomic molecules representing the FTIR graph. Thank you.